remember when you're looking at the recordings, right? So I have trouble with this camera. They did at least turn off the rezoom everywhere for me, but I'm still not sure it's great. So you have the slides, and then you have the video and audio for what goes on in class. So hopefully mixing the two. You might have to pull up the PowerPoint though if you're reviewing the video. So new unit, kinetics. So exam 2 will have kinetics and equilibrium. Now, to be honest, exam 3 is going to have more equilibrium than exam 2, but the way we're doing it is we're stapling kinetics and an intro to equilibrium, because when we get to exam 3, to unit 3 and exam 3, it's going to be about pH, and I'm going to go absolutely bonkers because I love talking about pH. So I don't want to beat y'all up too much with that. I want to put some equilibrium on there ahead of time. Plus, there's so much math in the kinetics side that you, I promise you, didn't want me making an entire unit out of kinetics. It would hurt. Okay. So chapter 12 in your textbook, please do read your textbook. Okay? Because there's so much in this, so much deeper. We're going to be able to go here. And I want you to think about where it goes with your future career. City, this kinetic stuff that we're doing here, right, is gonna lay the groundwork for peaking, right? If you don't have this stuff, when you go to Waz's PChem, oh my God, it's gonna be like, because he's gonna go way next level, right? Miriam, when you're talking to your patients about why do I have to take this drug twice a day at this, this dosage, and why can't I just take it once at twice the dosage? The answer is in the kinetics and in the decay processes. So it does affect where you're going, right? Have you ever wondered why? So what's the dosage, over-the-counter dosage for ibuprofen, right? For somebody my size, I take 2 of them, right, every 4 hours, right? Well, that means that I can take 12 of them a day. That works out? Right? Well, why don't I just take 12 at once? Why not, Miriam? This is in your world, right?
Like too much at one time.
Right. I mean, that's the same dosage per day, right? 12 of them at one time is the same as 2 of them every 4 hours. Right? Am I doing my math right now? Make sure I'm doing my math right. Why can't I do that? Somebody comes into your clinic and they're asking this, right? How do you answer? What would you tell them? But it's the same amount on my body. Well, why does it matter when I take it? Could I do like 2 tablets and then 20 minutes later do 2 tablets? And 20 minutes later do the next 2? You think it's about digestion. I get that. Okay, that does make sense to me. It's not about digestion. It's about your liver. So it's about decay processes, the kinetics of decay. So we're going to answer some of those questions for you, right? Okay, that you can take to the next level. Make sense? All right. Some folks have not taken the exam yet, and I did try to give back a little bit. Murph said that he noticed, taking the exam, that the 10 multiple choice were 5 points each, and the 2 constructed response were 25 points each, and he was afraid that not everybody noticed that, right? And so, Murph, I took what you were saying there last week, and I regraded this exam 2 ways. I graded it the way the points are listed on here, and then I changed it to 7 points each for the multiple choice and 15 points each for the constructed response. I've graded it both ways, and I'm going to put the better grade in of the 2. Okay, so when you see a grade go in, it's the better of those. Okay, all right. I don't want to do too much on this, because like I said, we have 2 people left to take it. Question 1 was fairly easy. Yes, you have yours. Was it? Some of the questions were harder than others, apparently. What's question 9?
Question 9 is solubility.
Okay. Okay, solubility on number 9. What should we quote?
That's the.
Yeah, okay. There was a practice, and on the practice exam, there was an example of this. And then, question 3. Ooh, question 3, y'all. Y'all remember the effusion question? Question 3, right? 23%.
Also, how many laws?
Say again.
How many
Question, right? Yeah. What did it say? Y'all, did question 3 look a lot like that right there in your textbook? Think we're gonna need to get into the textbook and practice a hell of a lot more, y'all. Okay, so, maybe y'all not had a course where it was this crunchy on needing to get into the text and really take it apart. So what's your process when you read something like this? Natalie, you did read chapter 9, right?
I read that. I look at the summary terms and then figure out what I don't know from that.
Don't, please, God's no. No. Go through the whole chapter, please. And especially the examples, because when I'm writing an exam, right, I'm assuming, well, looking at this, Mercy has seen this question, right? And I assume that she has worked it through, right? So this will be a good question to put on the exam. That makes sense. Okay, so the practice problems, I'm assuming that you're looking through them, and if anything in them is not like, oh yeah, right? And try, work it out, or come see me and Allison, right? This works it all out entirely, like step by step, right? Works it out for you. And then it has another one. So it's scaffolding, it works one out for you. And then it has this another one here. Then it's not worked out step by step, but gives you the answer to see if you can get there, right? So there's a lot of learning tools in that you can use, right? To step it up to the next level, right? You need to do that for exam 2. Please, please, please. Exam 2 is not going to be easier, y'all. See. Kinetics. This is what exam 2 is. So. Oh, okay. So when you see tables like this on the exam, I assume that it is not the first time you are seeing this. Okay? When you see problems like this, I assume that it is not the first time you have seen them. If it is the first time that you have seen them, then yes, you will do poorly. Right? Yes, the first time I saw it, I probably did poorly on it too. All right? First time I saw this, though, kinetics was God. So there's that. Yeah. All right. Terminology. Natalie likes this part of the text, right? Some terminology for this kinetics unit. When I use the bracket thing, as far as y'all are concerned, I'm going to mean concentration of a thing. So, like, if I just write concentration Ca2 plus, I'm talking about the concentration of calcium ion in solution. Okay? The little sub-zero, I will put stuff like that. I'll put subscripts like that, and I won't even think about it because I'm so used to it. But that sub-zero is pronounced naught, N-A-U-G-H-T, Old English for zero. And so concentration A sub-zero or concentration A naught means starting concentration. And then the sub-T here will mean concentration as a function of time. So it could be at 2 minutes or at 3 minutes or whatever, depending on where you're looking at it in reaction progress. All right? Please don't be confused by that, but stop and ask. Please do stop and ask if I say something like, I don't have any idea what you're talking about. So, we're going to do a lab next week, which Waz is going to cover. Because I'm interviewing at a different college next week. So, yeah. So, kinetics, he does love this one. You make it exciting, though. That'd be good.
Yeah, might be there all the time. Prepared.
So, and we'll talk about this. The constant, so look at my axes here. What do I have? What do I have here? It's concentration of something, A, just random, over time. What is happening? Looking at my graph, read the graph. What's happening to the concentration of species A? It does decrease over time, and then let's go deeper. Look at the shape of the curve. That's it. Okay? So, up until now, did Hagberg get to this in high school? Nice. Beautiful. So, in 2.1, you might say, well, hydrogen peroxide decays to H2O and O2. And you would do stoichiometry, how much, right? Well, now we're going to ask a new question. How fast? How fast does this reaction occur? I have upstairs in a lab, I have a bottle of 30% hydrogen peroxide, okay? It is dangerous because it's not, I've used 95% hydrogen peroxide before. 95% hydrogen peroxide, we accidentally spilled it on an aluminum well, a well casing, and the aluminum caught fire. Okay, so So if you pour 30% hydrogen peroxide on dry wood, it will probably catch fire. However, if you look in your medicine cabinet at home, do you have hydrogen peroxide in there? Yeah, probably 0.3%. Okay, and it doesn't. Now you pour it on aluminum, it bubbles because it is oxidizing, the same process as wood catching fire. It's just a much lesser version because of the lower concentration. But how long has that been in your battery? A couple of months, and it's fine. Do you have it in a refrigerator? You don't, and it's fine. And that's because of its concentration. That 30% upstairs has been there for 9 months now. In the refrigerator the whole time, never been opened. I'm not positive it'll be still 30% because it'll decay over time. So that's what we're going to be talking about, is how fast does something. And it's concentration dependent. Maths note for this. So again, calculus is not a prerequisite for this course. So do not feel like you have to have calculus for this unit. However, this unit really is about calculus. Okay, so we're going to dance around some of the ideas in calculus. Okay, so when I talk about, right, please don't hit me with something. Okay, when I talk about the derivative at a certain point and I talk about the delta y over the delta x, that's not correct. It's technically not a derivative. It's an average rate of change at that point. If I'm talking about a delta over a delta, right? So technically a derivative, you would have to use the limit as the delta x approaches 0, We can't do that yet. So we've got to approximate our derivatives. You can think of it as the slope at any point on the curve. Okay? It's actually not even derivative. It's actually partial derivative with respect to whatever the x-axis is. And please do remember this from Chem 1. If you don't, go back to your chapter 5 and catch up, or get me to catch you up. This idea of a state variable. My example for this is if Braden and I go up to, do y'all know where the watchtower or where the cell phone tower is on top of the bridge? Just west of the campus. There's a nice cell phone tower. You can see beautiful place to see sunrise and stuff. If Braden and I both go up there, right? Braden goes up along the road up past the Trade Center, right? And then parks there and walks up to the cell tower. And if I take off, right, and I go out the back door here and go straight up the ridge, right? And then go across the top of the ridge to meet him at the cell tower. Our elevation will be the same. Our change in elevation will even be the same, regardless of the path that we took to get there. Okay? And that's what's meant by a state variable, is that it is path independent, or right in terms of calculus, the circular integral equals zero. So it doesn't matter what path you take to get there, your difference is what matters. The endpoint minus the beginning. Another example of this, the orange curve represents a theoretical reaction, but the blue curve might be actually what happens. You might have an energy and it come down to an intermediate species, lower energy, and then after it reaches the intermediate, then it may come down to its final energy level. But you don't care. All you care is about the beginning point and the end point. You don't care if there was something in the middle. Does that make sense? Because the delta E would be the same for these two, for the blue reaction and for the orange reaction. You can ignore it. In fact, in real chemistry, we often don't know what the intermediate species are. And so we have to ignore them. We hope that it's true, that you can just ignore them because we think. Some more terminology here. Some of the intermediate species happen like this. There might be what's called a transition. Yeah. Sure. What you got? Before this, oh. Do you have an answer to that? Like this derivative of a circle? No. Okay, so that makes sense. Rid of this workers. That'd be good. Just go tell Vince that you want some videos. All right, so think about let's see. So go back to our story here. Braden drove up there to the Trade Center, right? Past Trade Center to where we were going to meet at the cell tower, right? And then his truck won't start. No, it's not. His Hyundai won't start, right? So, oh God, how are we going to get him back home, right? Oh, well, we're on top of the hill, right? So he should just be able to put it in neutral and go, right? Does that make sense? Or is it straight there? Knock it out of gear, straight. Okay? And just roll down the hill. But wait, what if he's off the side of the road there a little bit and there's that little lip at the side of the road? You know what I'm talking about? So if he just puts it in neutral, he might not roll down the hill. Agreed? We might have to both push to get it up over the lip, right? Onto the good slope, and then just jump in because it's going to do the rest, right? Well, same thing here. A lot of times, there's this little activation energy where my arrow is up there, that we have to do a little bit to get a reaction started, and then it'll take off and it'll reach the lower energy state. And a lot of times that is a transition state. That double dagger thing I have up there on the AB is called a transition state. And the E sub A here, we're going to need that piece, is the activation energy for a reaction. All right, onward. Oh, right, and if I come to MSLC and I ask, hey, algebra, college algebra, my professor wants me to be able to find the degree of a polynomial. Now, y'all all had college algebra, at least your transcript claims so, okay? So if I need to find the degree of a polynomial, what do I need to do? Look for the exponents related to any independent variable, right? Does that make sense? Okay, y'all remember that, degree of polynomials? Like first order is often also called linear, right? Second order, right? Called quadratic or parabolic, right? And then third order is also called cubic a lot of the times, right? Remember those? A little bit, okay. Well, I might want to brush up on them. Because now we're going to do these, but instead of just X and Y that you have no information about, I'm going to be giving you concentrations, times, stuff like that, even rates. We're going to actually apply derivatives, but we're going to lines that are not derivatives. All right. I give you the source here. I know that's crazy long URL. I'm sorry, but you can just copy it off of the slide. I strongly recommend looking at this text. Sydney, Natalie, Merv, who else is my chemistry major? Can I have one more in here? We're hoping Miriam, right? I'm not going to absolutely require y'all to go to that source, but oh my God, so strongly recommend it for y'all. Okay, this is a discussion of really what's going on here. It's where I stole a lot of this info from. Also, it's a free textbook, so it's good to have. Okay. All right. So we're going to talk about the rate order. Now, what did order mean a while ago on the polynomial thing? What did it mean for a polynomial? What's rate? What's order mean for a polynomial? Okay, well, can you maybe give me more words? Yes, it has to do with the exponent, but what? So let's see, I've got a function here, f of x equals, let's say, 3x squared plus 2x, right? And plus 5. All right. Space, make stuff up. All right. Now, do you want to see what the behavior of this function is? How would you graph this? You're looking at, you remember having to look at the different types of functions in ninth grade algebra, right? You had, and you had, right? Remember that? Remember those? You had an end-of-course test in Algebra 1, where you had to be able to identify those things. Remember that? Yeah? Which one would we put with this? And why? Why? Wait, this one? Why?
Because it's quadratic.
Okay, so this is the y equals x squared curve. You agree? Yes? Oh, what's this one? Well, then why would you pick it? Why?
To determine the shape.
How does it determine the shape? Yes, it does. You're on the right track. Keep going. Why?
Anything else you do to it won't affect it.
It won't be important. It's gonna get buried in that square term, right? Yes, same idea here. We're going to be looking at what the behavior of our chemical function is. Okay? All right. So, looking at those curves up there on the top, that's what I want to talk about. Is what order those curves. Okay? Does this make some sense so far? Please digest it because I'm about to throw you a curveball in just a minute. Okay? Are you digesting? Good so far? Yes.
Are we gonna need to memorize the units of K rate constants for the zero first and the second?
So my short answer is no. Let me think about this for a second. Answer to that is you're going to have a cheat sheet, right? I think it would be a good thing. But the reason it's not a simple note is because having those in your head when you're trying to deconstruct some of these problems, actually it's a really good tool. So it might be good I'm going to use a term that's ill-defined here, to know them rather than to memorize them. Does it make any sense?
Yeah.
But for the exam, I would definitely want them on my cheat sheets. Yes. Does that make sense?
Would you recommend putting all of this stuff?
Depends on where you are. These, I definitely. And then the integrated rate laws, that line between, I definitely would. But I have seen a lot of people want the curves. So, does that make sense? No, it depends on where you are specifically. But I'm going to do more on this. Not just this slide, I'm going to do more on this in a minute. Okay. Again, gotta read your textbook on this because it's going to spend significant pages. Or electronic. I don't know how pages work it out, but it's going to spend significant amount of space on this idea. So the negative and the positive we use, and I'm gonna say this even though other chemists are gonna hate on me for this, we use this very poorly in chemistry. And I'm sorry, but none of the rest of the chemistry community cares that I think we use it poorly. They're gonna continue to use it that way. The negative is just gonna mean that it's a reactant and is being consumed, and therefore the concentration is going back over time. And the positive version means it is a product, and so the concentration is going up over time. Does that make sense? So when you're doing your rates, this is going to be another of those things where we don't care if it's negative or positive, right? All we care about is how fast. So in physics terms, it's a scalar that we're after, not the vector. Okay? The vector just applies whether it's a reactant or a product. Does that make sense? Okay, now let's look at your units here. So look at the units on this guy, right? What's going on with that?
Is that molarity per second?
It is molarity per second. So let's make that make sense in your head first. What's going on with molarity per second? What's happening? Concentration over time is exactly right. So remember, how do you determine slope in algebra class? How do we, M equals what? How do you calculate slope in algebra class? Well, that's the slope-intercept form. How do you calculate the M part of that? Yeah. Delta Y over delta X. Change in Y over change in X. Well, this implies then, Aiden, right? You said it was what? Molarity over seconds. So concentration over time. So delta Y must be what in this case? Molarity. So we'll take one molarity at one point in time, subtract the molarity at another point in time. That's delta Y. Over what, Aiden? Seconds. And what's the denominator of the slope equation? So it must be what then? So the y's, we took the concentration at one time and subtracted the concentration at another time. For the x values, we must be subtracting that time from the other time to get a number of seconds. So concentration, change in concentration over change in time is my delta y over my delta x. Does that make sense? Maybe? Not talking to you. I said math. See, I speak in that math language and then I stop talking to you. I don't know. Okay, graphical presentation, okay? Remember that, so when I put these animations in the PowerPoints, if you just use the preview function in Georgia View, you cannot see any of the animations. If you actually download the PowerPoint slide, then you can, in fact, see the animations. And so you can see more of a kinesthetic version of this. So A is my reactant here, and B is my product, and I've got them color coded here. My reactants are going to be black, and my products are going to be red, right? So we have all black, and over time, do you see what is happening? What's happening here in the animation? Yeah, the black dots are becoming red dots. Right? But that animation, that's supposed to, I should have used digital. That's supposed to be a clock up top. That's supposed to represent time. The little circle thing with the dot, that's, I'm sorry, it's a clock, but there's one. Okay. I know it's archaic, but, okay. So change in concentration and change in time. I can graph them. You know I'm going to graph them, right? Because I graph everything. What's happening? Now wait. Y'all said this earlier. Let's look at the black curve first. It represents the black dots. What am I showing on my curve here? The number of molecules or the concentration is decreasing over time, right? Well, wait a minute. What am I showing with the red curve then? The molecules of B, because they're a product, are increasing over time. Does that make sense? All right. You going? Very good. Okay. Reaction rates and stoichiometry. My homework questions always trip people up on this, so know that something's going to be coming on this. So think about this. Look at my stoichiometry. I've changed my equation now. New reaction. 2A. React to form 1B, right? Tell me about their rates. How fast does A get used up compared to B forming? If, let's see, let's say I've got a concentration of A here. I'm going to make a table, and I've got concentration of B, right? And let's see, time 0, we've got 100 molar, this is molar. 100 molar A, we've got 0 molar B, okay? After 5 seconds, pick me a concentration for A. Murph, what's my concentration A? Keep it simple, please. Pick a random number. Okay, 75. Cool. What's my concentration of B? I disagree. Stoichiometry. Digest this for a minute. Talk to me. If it is cryptic how I came up with this random number 12.5, it wasn't random this time. Murph 75 was random. But my 12.5 now, after Murph picked his 75, I have 0 degrees of freedom. I had to pick 12.5. I have no choices. Why? He's trying to make words. I know. What is the delta concentration A here? How would you figure that? Okay, so it's what? 25. Well, delta concentration B. How, if 25 moles of A got used up, right? Look at my stoichiometry up there. What does it say? Okay, it's a 2-to-1. Therefore, 25 molar A right? So geometry is the key to everything in chemistry, y'all. If somebody did not teach you, I'm going to pick on you again because I know it's not true in your case, right? So if somebody that was supposed to teach you stoichiometry did not do so, but she did, right? But if she had not, you should be going to yell at her, right? You don't have to yell at her because she did teach you. Plus, you don't want to yell at her. All right, so does this make sense? Please stop me now if it doesn't, because I'm about to make it more complicated. Does this make sense? Anybody want to stop me yet? Am I good, Ellison? Okay, well, if we can guarantee that about that 2 and that 1 up there on the A and the B, right? Then I could generalize this idea to all of these stoichiometric relationships, the A, the little b, the little c, the little d, right? And I could make a rate relationship here that looks like this. Does this make sense? Okay, Miriam, it made sense where? Where do I? Let me go back, hold on. Did it make sense here? I'm doing the same thing. What was the stoichiometry in front of the A up there? Okay, and the stoichiometry in front of the B, it's just the 1. So that's this little a, 1/2. See that? Make sure. You know I want you to have a D, right? Okay. Yeah. Good. Talk to you. You gotta use your words. You gotta get me to tell you what you don't know. It's a lot of looking at it. All right. There's a lot of things going on that slide. I agree with that. Yeah? Good. Kara, happy with this? Okay. All right, example. I do this well. Yes, Miriam likes it when I put it into an example, right? Okay. What should you do first here? Yeah, say it louder, you're right. Balance it. It is not balanced. All right, I'm trying to do that thing. Who was telling me to do that? Natalie was, I think, telling me to talk through my process, right? Okay, so I'm thinking I need to check my balance first. Let's see, we've got O2 goes to O3, ozone is O3. Let me see, it's not balanced. So what do I want to do here? What do I want to do to balance it? You don't want to do what I want to do, use fractions. I want to use 1/2 in front of the O2 and 1/3 in front of the O3, but y'all don't like that. So how would y'all like to balance this? Yes, Owen? Put a 3 here. And, yeah. Okay? Happiness so far? All right, you got to check your balancing. We got that over there. And we've got this idea right here. Now, I'm going to tell you my thinking in this. I make up a thing that doesn't exist. So this rate, I think I'm not the only one, because I stole this either from your textbook or from another one. I think I stole this one from Chang, but not sure of that. This idea of rate. I'm going to calculate my rate as in concentration of reactions. Well, that's not a real thing. It's the concentration of the species that are real that we can measure. But I'm thinking as if, see the arrow up there in between the oxygen and the ozone? I am thinking in concentration of arrows. Okay? And that will be this rate of my reaction right here. Well, that rate is equal to negative 1/3 the change in concentration of O2. Why is it negative? Because it's being used up, because it's a reactant. Does that make sense? Okay, so why is it 1/3 instead of 1/2? Well, you told me to put it, the answer to this question. Why is it 1/3? What did you tell me just a minute ago? Would you help me with it? Because of the balancing. You balanced it, what was the coefficient in front of the O2? So the denominator of this guy is your coefficient. Does that make sense? Yes? So here, this 3 is this 3. Okay? And so on the other side equals 1/2 the concentration change for ozone over delta T. But it's 2 because the coefficient of that is 2, and it's positive. Why, Kara? It's not being used up, it's forming, right? Because it's a product. It's being used. Make sense? All right, fine. So now we have a problem. Here's our example, Miriam. I know that the rate of disappearance of O2 is 150 millimolar per second. What is the rate of appearance of O3? So we have our equation there. What would you like to do to set it up? Sydney, how do you want me to set it up? What pieces of that green up there do I need? What do you want me to start with? Well, you're going to have this problem in homework. What are you going to start with? Marcy, what are you going to start with? Into what? I don't have anything to plug it in yet. You want me to write an equation first? What do you want me to write first? I want to do step at a time, right? Okay, so what do you want me to write up here to start with? I think we need my rate thing out there on the far left. I don't think we really need it. So this guy out here, I don't think it's going to get involved. Because what are we asking about here? We're asking about O3, right? And we're given O2. So the overall rate is not even being asked about. Does that make sense? So what pieces do I need to write, Mercy?
Negative 1/3. Delta O2, that'd be 150.
It will.
Over 1/7.
Good. I'm going to go ahead and write that, but you are correct. Okay, so what will we go on the other side of the equal? 1/2, okay. Positive or negative?
Positive.
Why? Because it's problem. All right, cool. Now you're saying I could replace some of the pieces here? Okay, do I keep this? Okay, so keep the negative 1/3. Okay.
150.
The delta T part,
Delta,
delta O2 part is 150 millimolar, E-3 molar, it doesn't matter, however you want to write that, okay? Same thing. What about this part? Oh, good, good, okay, I don't think that's automatic for everybody. It says 1 millimolar per second. I want to make sure everybody sees that that is 150 millimolar over 1 second. Okay? What's your then what? And then what about do here?
concentration of 3, right? So that would be one of solve.
Okay, so 2 ways you can look at this, and I want you to tell me which one you like. Are you going to be solving for the numerator here, delta O3, or are you going to be solving for the entire fraction here? And either way is valid. Just whichever way you want to look at this. Okay, if we're going to do that, then we need to go ahead and decide over how many seconds. Say again? That is the correct way to assume. Same as this one over here. Okay? So if you're going to do this in 1 second, you should probably also do this one in 1 second. Does that make sense? You could have said, let's just solve for the entire fraction at once, and that also is a valid approach. Okay? If we're set up now, right? How many variables do I have left here? Just this one. Delta O2, delta, yeah, O3. Delta O3, yes?
So what should be negative if we're losing it?
Yeah, that's what I dislike about the way we use this. The way you were thinking is the way I would have done this. I would have not put the negative there, and I would have put the negative 150 here. They don't. They say scalar concentration change, put the negative out here. It doesn't matter which one you do, don't do both. Okay? That makes sense? I agree with you. All right, well, we still have one, we have one unknown, right? What's our unknown here? How much does O3 change in 1 second? Well, how do we solve for it? How would you solve, if you're in math class, right? Cindy, you're sitting in your Calc 1 class, right? How are you going to solve? How are you going to solve? Right there. How are you going to solve this? No derivatives or integrals required. Don't go too deep. It's just the algebra part. What do you want me to do?
Multiply something.
Multiply this or this?
The O3.
Multiply what?
The O3
This side? By what?
itself. Cancel out. Cancel the numbers.
What do you want me to put out here?
I forgot algebra.
Can I, by 2? Carol, why? Why are you multiplying by 2?
It gets rid of that half.
Good. Multiply by the reciprocal of this. Right? Also, might want to multiply by this 1 second here because it's in it. That make sense? Yes? Can you randomly just multiply by this period? As long as you do exactly the same thing to both sides, right? So the 2 cancels, 1 second is canceled, the 1 you don't care about. What happens over here? Anything else? So what would you like to do to clean this side up? What? Yes.
Is that 3M a unit or is it included in the equation?
150 million. The molar part is the end. That help? What do you get? Do that when you hit, right? Okay? Right? I know it's gonna hurt. You don't care. 100 millimolar per second. Okay? It's a scale. You don't care whether it's negative or positive, right? You get hit by a car going 20 miles an hour, you do not care whether it was going 20 miles an hour forward or backwards. It's a scale. Don't care. Okay? It rates. Okay? Make sense? Good. Oh, come on. Do it right here. You want to come drive? Oh, you can. All right. All right. Does this make sense? Now just walking through, does that help some? All right, cool. You show me. This looks more like one of my problems, doesn't it? Old words. Does anybody want to take a picture of that guy before we get rid of it? Because we're going to want the cord. All good? Oh, Mark's good. If y'all need one later, Mark's got it. Good discussion. Can you have that discussion out loud for everybody? Because it's a very good one to have here. Please. You're not the only one, I promise. Please talk out loud. All right, let's see. Hydrogen gas. What do we want to start with? What do we want to call in my equation? Right? Ready? Did this mess people up on the exam? The two part? Okay, good. Then what? Plus O2. All right. All right, now, what are you thinking it becomes? That is correct. It will become H2O. What should you check? Is it? No. All right? So you can balance it this way. All right. If you're brave, if you've been taught somewhere to fear fractions, because most of you have been, how would you balance it instead? That also works. Okay. All right. What would you like to do now? Oh, and what will be your next step? Lori, what do you think? What's confusing with this question? Because I honestly don't know that. Please tell me. Please tell me what's confusing.
Would we need to define a layer using?
Okay, now you got it. All right, good. Thank you. Thank you, David. That's what I need to know. Remember, there was a little tidbit when we started about gases, about gas stoichiometry, that you can just do it in liters. Okay, so liters per second here works the same as molarity per second. Does that make any sense? Okay, thank you. Does that help clear it up then? Okay. Given that, then where do we want to start, Ada?
You make the equation.
This one or what do you want to write?
So on the left side, you write -1/2,
1/1/2.
because it's joules of
Okay.
Kelvin. And then multiply it by maybe 35 H2 over 1 second.
Like this? Which one? Okay, all right, coming to the other side now, what would you put there? Move on, no, I gotta get you there.
Okay.
So Ada gave us this, right? What goes over here on this side? Where did Ada get this to? So then, what are we looking for in the problem? Oxygen, so we need to look where for our coefficient? Which is, so what goes here? Makes sense? And then what goes in this parentheses here? Yes, Mary?
It says if the rate of formation of water is 35 meters per second. How would you do that for the water?
Oh, you wouldn't? You want, so this doesn't need to be H2, this needs to be H2O. Do we need to change this to? That help me? Thank you. Huh? She's awake. All right, what do we do? What would you like to do here? Cindy, can I come back to you for algebra again? Is your algebra back awake again? You what?
Cancel everything down.
How? What would you like me to do?
1/1, you don't have to cancel it out.
Okay. Multiply by the reciprocal? This makes it feel better, you know. All right. So. Yes?
So do you not do anything with H2?
You don't have to. I thought we were going to, but Miriam fixed me, remember?
So other than moles or liters, what else do you do? Is it just moles?
Partial pressure, what else might I say? Technically, you could see molality, I doubt you will in this course, but you could see molality. So any kind of concentration, ppms,
So you would have to convert it, you just plug it.
say it again.
You would have to convert it, and just plug it.
No, you don't have to convert anything as long as you're cool with what you're solving for having the same units, then you can kind of just ignore it and just keep it in the same units. Does that make any sense? Right, you could have milligrams per liter or something like that, yes. But then really, I would definitely say just don't change it, just have your output be in the same kind of units, and that way you don't have to worry about it. Just like when we're doing C1V1, right? When you're doing the dilution, C1V1 equals C2V2. And that concentration, that C1 and the C2, can be in any units you want. ppm, milligrams per liter, molarity, molality, you don't care as long as they're both in the same. Does that make sense? All right. All right. Concentration, mathematical rate, yeah. Those are derivatives. I know that really it's derivatives, but we're going to treat it as if it's the deltas, okay? do we know? How do we know these rates? We watch them change with an instrument. Okay, and so we will actually put them in a machine and watch the color change over time. Or there are plenty of other machines that we might measure the magnetic response or the atoms response, you might count the atoms even, stuff like that. Like we watch it change over time, and that's how we get these rates. This is going to be important in your homework. So one last thing before we go. So when you want to calculate the slope at a point, as far as you're concerned, don't take a derivative, just take the closest points to it. So if you want to know what the rate of change at 50 seconds is, you could use 100 seconds minus 50 seconds, or 50 seconds minus 100 seconds, or even 100 seconds minus 0 seconds to approximate across that interval. Okay, and that would be your delta BR2 in this case over your delta T. Okay, remember to divide, because if you do 0.00846, you use the pointer. 0.00846 minus 0.0120, that is over 100 minus 0. So your rate is not that delta BR2 over 1 second. It's that delta BR2 over 100 seconds. So to get the change per second, you have to divide by that 100. Okay, get in there and practice. I don't know if there's homework up yet, but if there's not, there will be soon. When do we have to do tomorrow night? Yes. All right.
It's like when I have to do, you know, they do that, it's like next question.
Yes,
It's like they're going to do it.
I know.
It's so awkward to work with.
It is, isn't it? Hang on, Braden, don't answer this yet. Stop recording.